It's really exciting to be back, especially hearing that, as you mentioned, that this will be I am the first ever person to do 2 Royal Institution live streams, which is really awesome. And I'm very humble and grateful to be back. So thank you everyone for wanting to hear more about the Millennium Problems. So I will be covering the 3 remaining problems that we didn't quite manage to get to last time. But I will give everybody a recap of what the setup is and what those problems are that were covered very quickly last time, just to make sure that we're all on the same page. Okay, so the Millennium Problems, they are the $1 million equations, as the title of the talk says. So here is a case of $1 million, and I'm again wearing my $1 million t-shirt, which I also had on last time. So the idea was that in the year 2000, the Clay Institute, an institute in the US who have lots of money, wanted to use some of this money to help promote mathematics and help to encourage more people to engage with maths research. And one of the ideas they came up with in order to do this was to create the Millennium Problems. So this was the year 2000, when lots of things were happening around the millennium. And they decided on 7 problems, which were deemed to be the greatest unsolved problems in mathematics at the time. And they set these prizes up such that anyone who could solve one of these problems would be awarded $1 million. Now, to be considered to be a problem, you had to satisfy this very vague criteria, which was that it had to be a classical problem that had resisted solution for many years. So there's lots of interesting things I can say about this, but the main thing for me is that it doesn't mention that this must be an applied problem, or that the maths must lead to a change in the world, for example. That there's no sort of, there's nothing there saying that it has to really affect people's lives. It's basically just saying we want really hard maths problems that are interesting mainly to mathematicians. And if they happen to do other cool stuff, that would also be nice. But really, it was really difficult, really fundamental maths problems that were considered and made it onto the final list of 7. So the ones that I covered in the first talk, and you should definitely go and watch the YouTube video of the first talk, but I will very briefly summarize them for you. So we did the Riemann hypothesis, perhaps the most famous of the Millennium Problems. And this fundamentally is asking about our understanding of the prime numbers. So a prime number is something that's only divisible by itself and 1. It has no other factors that will go into that number. For example, 7 is a prime number, but 9 would not be, because 3 times 3 would give you 9. And this, well, we don't really understand the distribution of the prime numbers on the number line. They seem almost to not have a pattern. And the Riemann hypothesis, we think, gives us some clues as to what that underlying pattern might be. So as I said, this is the most famous, I think, of the Millennium Problems. It's also, I believe, listed in the Guinness Book of World Records as the world's most difficult maths problem, where they judge that based on the number of unsuccessful proofs. So more people have tried to solve this than any other maths problem without succeeding, which I think, according to the Guinness Book of World Records, makes it the most difficult maths problem in the world. So we've got Riemann. The second one that I discussed last time is P versus NP. This is all about algorithms and sort of how computers work, how computers solve problems. And what the question fundamentally asks is, we have 2 different types of problem, those which are easy to check the solution for. So it's easy to mark. Someone gives you a solution, you can very quickly check if it's correct or not. And those problems are called NP problems. And then we have P problems, and they are problems which are easy to solve in the first place. And the P versus NP Millennium Problem asks, are these 2 things the same? Does P equal NP, or are they different? And you have to be able to prove this in order to earn your $1 million. The third one we talked about, my favorite, totally biased because I study fluid mechanics, is the Navier-Stokes equations. So this is a set of equations which describes the motion, the behavior, the properties of basically any fluid that you can think of. And when we say fluid, we do include gases, are fluids as well as liquids. And we have a set of equations that describe what's going on, and they work. They're used by physicists, engineers all the time. The issue is we don't really understand these equations mathematically. And that's what I mean when I say, are they well posed? That's something that we can't answer as mathematicians. We can use the equations, do really cool stuff with them, but we just don't really know. We haven't gotten to the bottom of what's going on, like hidden in that complex maths. So if you help us understand that, you could potentially get the $1 million prize. And then the fourth and final one, this is the one that was solved, which is why everyone was so excited to hear about it last time, which is the Poincare conjecture. It was solved by Gregory Perelman, this Russian mathematician shown here. So he solved this in 2002, and he then actually refused the $1 million prize. So it's a very interesting story in itself, and I talked through the whole story for everybody last time. But this is to do with four-dimensional objects and topology, and it kind of asks if I have something that's smooth and finite in 4 dimensions, can it be deformed to a 4-dimensional sphere? So it's quite an abstract problem, but it's quite a famous one because it's the one that's been solved and the only one so far that's been solved. So the other 3 that I just mentioned, Riemann, Navier-Stokes, P versus NP, currently all unsolved. The 3 I'm going to talk about tonight, currently all unsolved. So there's still $6 million available for anybody who really wants to have a go at this. So on to this evening. So we're going to do the voting again. So I am going to cover all, but I think it's nice to let the audience, let you all decide the order in which we cover them. So there is a first poll now, which hopefully if you click on polls on the panel, you'll be able to cast your vote for which one you want to hear about first. But as I said, you don't need to panic too much because I will cover all 3 today. So we've got the Birch and Swinnerton-Dyer conjecture as the first one I've got here. This is all about things called elliptic equations, which is a particular type of equation. And it's about figuring out when they have rational or fraction solutions. And these are very important in cryptography, which is why I have a picture of an iPhone, because elliptic curve cryptography is actually used to encrypt iMessage. So if you've ever owned an iPhone and used Apple's iMessage service, or even used it perhaps on another Apple product, then you've actually interacted with elliptic curves without realizing it. And that's what Birch-Swinnerton-Dyer conjecture is all about. We've got the Hodge conjecture. This is incredibly abstract, to put it politely. You'll see when I talk about this, but this is by far the most inaccessible of all of the Millennium problems. I will do my very best to explain as much of it as I can for everybody. But fundamentally, it's asking, we have some particular objects that we are interested in called Hodge classes. And the conjecture says, can we build them from smaller, simpler pieces called algebraic cycles? So it's kind of asking, like, can we build more complicated structures from simpler pieces, which is why I've got a picture of Lego. Because in Lego, you take simple pieces and you build castles and pirate ships and all kinds of cool stuff. So that's the Lego one, Hodge conjecture. And then the third and final one for you to vote for will be YangMills and the mass gap hypothesis. This is all about quantum theory and how we are trying to mathematically describe what's happening in things called quantum fields. So this one's very physicsy and very much to do with quantum, is what we'll be talking about there. Right, so I think the poll that you've all been voting, so I will go and have a look at which one is the current lead. Right, I'm hoping everyone has now voted. We've got YangMills running away with it, I think, with 50-odd%, 51%. And I predicted this, actually. Right, so YangMills is going to be the first one. So as I said, this is all about quantum theory. I've got a artistic representation here of quantum teleportation is the idea behind that image. So the YangMills mass gap hypothesis, one way of interpreting this is it's kind of asking the question, why do things have mass? And this is where the mass gap aspect comes into it. So it's the idea that the theory itself is predicting that there are no massless particles. Such a particle isn't possible. Everything has to have some mass. And so that's kind of why you can perhaps put this like philosophical spin on the question and say, why do things have mass? But to really get into the actual maths and the physics behind it, I'm going to start by giving you all a bit of a history lesson in sort of where we're at in terms of physics and in terms of understanding and the quantum world. However, I do have a very short clip which doesn't have any sound, so I will just play this. So this is a clip from Ant-Man, one of the Marvel movies. And this is where Paul Rudd, who plays Ant-Man, he clicks his little clicker to shrink down to Ant-Man, but he continues to shrink. His button was broke, and he continues to go smaller and smaller and smaller. And he sort of shrinks so much that he enters the quantum world, as they call it. They refer to it, I think, as the quantum realm, which is sort of this crazy world where space and time no longer make sense. I think in the film, he's kind of supposedly trapped down there for many years, but when he comes back out, he hasn't aged and all these things. Like, obviously, it's Hollywood, so it's not really based on too much science, but it's an interesting concept that we see the quantum world, or one of the ways we try to interpret it is almost as like an actual different universe, or like a different realm to you know, the ones as humans. And I will come back to that point, which is why I wanted to just start by showing you that little clip. But as I said, we're going to do a bit of a physics history lesson. So I've got a quote here, which is attributed to Lord Kelvin from the 18th century or 19th century. I think it was the 18th century, which says, "There is nothing new to be discovered in physics. All that remains is more and more precise measurement." Now, this is quite unfair to sort of call out Lord Kelvin on this, because he did loads of amazing stuff. But this was the general belief of physicists at the time, because what had happened was we had the work of Newton, we had Newtonian mechanics. So this is thinking back to Newton's three laws of motion, for example, you know, force is mass times acceleration, that kind of idea. All of that work from Newton had been done. We'd understood it. And for pretty much any situation that physicists in the 18th century could come up with, it fit, it worked. So it was reasonable to sort of think as a physicist, we've completed physics. Like, we've solved it. We've got the theory down. We've got the equation. You know, some of the stuff didn't quite work, but it's probably because we don't have accurate enough measuring instruments. And that was the general belief at the time. Now, slight tangent, but it's really cool, so I'm going to do it for you all, is these two physicists / mathematicians, Newton and Lord Kelvin. So I am actually mathematically related to both of them. And what I mean by this is there's this thing that exists in the maths community called your maths genealogy. It's a really cool project. And basically, if you do a maths PhD, then your PhD supervisor is seen as your like father in the family tree, or your mother. And then you can sort of trace their supervisor back, and you create your sort of maths family tree with branches. And so I actually did mine the other day, and you've got me right up at the top. And then around here, you have Lord Kelvin, and then right down towards the bottom, you have Isaac Newton. So this is just pure coincidence and a bit of a tangent from my story I'm trying to tell, but I thought it was pretty cool. So I had to share it with you all. So when I said some of the measurements we had didn't quite agree with Newton's theory, one of them was the orbit of Mercury. So Mercury, of course, the closest planet to the sun. You have a prediction of the shape of this orbit from Newtonian mechanics. And then if you measure using the instruments available at the time in the 18th century, it didn't quite match. Like, it's super, super close, but, you know, there was a little bit of discrepancy. And physicists at the time thought that was because they didn't have good enough telescopes. However, it turns out that now we have better telescopes and it still doesn't work. So there's potentially, you know, it's only a small issue, but there's something possibly going on there. And then one of the other things that sort of also didn't quite work with Newtonian mechanics and that understanding of physics was black body radiation. Here's a diagram showing you various wavelengths of light and their color temperature. So an idealized black body will theoretically absorb light of all wavelengths, which means that it should output an infinite amount of energy, which of course isn't possible. So that was also a slight discrepancy that physicists in the 18th century couldn't really resolve. So they seem like small problems, and that's why they thought, oh, it's just because we haven't yet got good enough measuring instruments. However, to fix the first puzzle, the orbit of Mercury, we basically needed Einstein and the theory of general relativity. So the reason Mercury's orbit isn't quite the perfect ellipse predicted by Newtonian mechanics is because Newtonian mechanics doesn't account for the curvature of space-time. So you have your sun, very massive object, and then you have Mercury is close enough to the sun that it isn't moving in a plane anymore. It's moving on a curve in space-time. And so that's with that modification and Einstein's theory of relativity, suddenly we have a perfect prediction of Mercury's orbit. So it seemed like a small issue, possibly because our telescopes weren't good enough. Turns out you just had to invent modern physics to actually fix it. And the second problem was similar. So to solve the issue with black body radiation actually required the invention of quantum theory, or the discovery, depending on your philosophical belief. I'll probably switch between invent and discover, but anyway. So the invention of quantum theory, and the way you resolve that one was the fact that light, shown here by this wave, made up of small particles. So light behaves both as a particle and a wave. And what that means in your black body radiation situation is that instead of absorbing light of all wavelengths, light is actually absorbed in quanta, or packets of energy. And that's quanta, that's where quantum theory comes from. So in order to fix these two tiny issues that physicists had in the 18th century, we literally had to invent modern physics. Quantum theory it's weird, right? I teach quantum theory to my second year undergrads, and like I absolutely love it, but just some of the stuff that you find out in quantum theory, it's just very, very difficult for us to grasp because it's so different to our experiences in sort of the medium-sized world that we're in compared to this subatomic quantum realm. And one of the ways in which it's weird, as I mentioned here, was this idea that light behaves both as a particle and a wave. And you have the very famous double-slit experiment, sort of shown here in this animation, which is this idea that if you imagine light here shooting these particles, all these dots coming through, as you're viewing them from one perspective, light is behaving as a particle. So you have two slits, and all you see are marks where the balls or the particles have gone through the slits. However, if you observe from a different location, what you see instead is this full wave pattern. So that's much like if you have waves on water and you have a water wave hitting a grate or a grid, you actually get this sort of spreading out pattern on the far side. So we have the whole, quantum basically is very peculiar and very difficult for us to grasp what's going on. That's often why it is pictured as a quantum realm, like, for example, in Ant-Man. So just to sort of summarize where we're at, we've got general relativity, which is for large, fast-moving objects, e.g. planets and stars. If we move down to sort of our scale, so I've called these medium-sized objects, such as people and billiard balls, the classic example of demonstrating Newtonian mechanics. Then we use Newtonian mechanics for that sort of middle-sized objects, like sort of our lives in some sense. And then on the very small scale, subatomic scale, like e.g. electrons, quarks, those kinds of particles, we have quantum theory. So this is kind of where we're at in terms of modern physics. And the YangMills problem relates to a process called quantization. So whilst I've drawn the arrows going down here, as in going down in size, what should actually be true, and what we are finding is true, is that you can take quantum theory, so everything that's happening on this subatomic scale, you can take what we know about that, and you can actually apply it and have it explain everything happening to medium-sized objects. At the moment, we don't think it will go up any further, right? That's kind of getting into the discussion of the grand unified theory of physics. So at the moment, it definitely, as far as I can tell, right, we don't really have any insight into whether we can go, quantum will do all three. But we definitely know, or at least through the various work that's been done, that quantum theory will actually work on this middle scale. And this process of replacing Newtonian mechanics and Newton's laws, replacing them with quantum laws, is what's called quantization. So that's currently happening in maths and in physics, trying to take what's happening in quantum theory and what we understand there and use it to explain medium-sized objects and the physics of our sort of the world that we experience. Now, the things that we can do, finite degrees of freedom. So, for example, if I have like 4 interacting particles, then each particle will have a position in 3D space, and it will also probably have a velocity and maybe a couple of other parameters. But in total, there's going to be a finite degrees of freedom to that system because I have, say, 4 particles or a finite number of actual particles. And that whole branch of physics, maths, is called quantum mechanics. Now, from finite, you can then do infinite degrees of freedom. And here, I'm giving the example of an electromagnetic field. So here, I sort of picture in my head doing an experiment at school where you have a magnet and you create the magnetic force field lines with the iron filings on the piece of paper. Such a cool experiment. So I sort of picture that. And what's happening there is because you have a magnetic field, electromagnetic field, like you can no longer, like your degrees of freedom becomes infinite because you need to describe the entire space itself. So it's like the whole plane needs to have like a coordinate, and the plane is infinite, you're getting infinite degrees of freedom. So finite degrees of freedom, quantum mechanics. Infinite degrees of freedom, it's called quantum field theory. We're almost there. Within quantum field theory, we have YangMills gauge theory. So, and this, we believe, is a very good candidate for describing the interactions between quarks, which are small fundamental particles that make up electrons, protons, neutrons, and also the strong nuclear force, which is the force holding together the center of an atom. So, just to kind of recap, we've got this process of quantization, which is taking quantum theory, everything we know about quantum, and using it to describe the real world, the world around us that we can see. Finite degrees of freedom, we've got quantum mechanics. That's a big tick. We know what's going on. Infinite degrees, it's called quantum field theory. That's way trickier. One of the methods used to currently try to understand it is called YangMills gauge theory. And it's very important for quarks and strong nuclear force. Now, the final part to understanding the YangMills millennium problem is to think about your EM spectrum, electromagnetic spectrum. So we've got, I've just written 3 possible components here. So we've got UV light, visible light, and infrared. So you've got, at the top, you have your short wavelength going down to longer wavelength. So at the top, you've got higher energy. So it's in decreasing energy order. Now, within YangMills gauge theory, when we're working with, and this is where we're talking about electromagnetic fields, which is why the EM spectrum is relevant. So within UV, high energy EM waves, we understand that using a process called perturbation theory. And that's just a particular tool that physicists use. It works. It explains what happens in experiments pretty much perfectly. So physicists are like, this is awesome. We're going to use perturbation theory when I have a high energy electromagnetic field. Now, when I have a lower energy one on the infrared side, we use a different theory. If you're a physicist, you use lattice gauge theory to do this. So the $1 million problem, the YangMills is basically to say, well, this is the EM spectrum, which is continuous. You just increase your wavelength as you move down in the way I've shown it here. So there's no reason, from a mathematical standpoint at least, there's no reason why we should have different theories for different wavelengths or different energies. So the YangMills question says these should actually basically be the same theory, but at the moment we can't connect them. So the way to earn your $1 million is to do two things. Final slide. Number one is to define YangMills theory in 4 dimensions. So 3 spatial dimensions and time. So you have to, first of all, come up with what that theory is, much like Einstein came up with relativity and much like quantum theory was born in the early 1900s. You've got to come up with 4D YangMills theory. And not only that, you've also, using your brand new theory that you've come up with, use it to prove something called the mass gap property. And that is what you have to do for your $1 million. So that's as good as I can explain that as a non-quantum physicist for you all. So I hope that was enlightening. And I will now open up the second poll of the evening for the remaining 2 problems. So we've done YangMills, or at least I've attempted to explain YangMills for you all. So now we've got Birch, Swinnerton-Dyer, and Hodge remaining. We will do both, but please pick which one you would like me to talk about next. And both of these actually have exercise. I'm going to actually set you a little exercise to do during both of these sections. So get yourself also, if you vote first, and then make sure you've got pen and paper so you can try and solve a couple of simple problems that I'm going to set for you all as well. So Birch and Swinnerton-Dyer is about elliptic curves, which is a particular type of equation, which I will show you examples of and explain. Hodge conjecture, super abstract, talking about building complicated things from simpler pieces, in short. 3, 2, 1. Right, it looks like it's the Hodge conjecture. So I didn't predict this one would be next. But I said I was trying to set my slides up, so I'm going to have to go over and change my slides. So well done for not conforming to what I thought you might all vote for. All right, so Hodge conjecture it is. Right, so as I mentioned when I was first introducing the problem, we have a particular system of equations, and we want to know whether the solution to that system of equations can be made or can be built from simpler pieces. So that's why I have this picture of Lego. It's about thinking we've got simple building blocks to make very complicated structures. And this is actually a really powerful tool in maths. So whenever you have some very complicated object or some new object that you've just discovered, one of the best ways to try to understand it is actually to be able to explain it or be able to show that it's made up of simpler pieces or smaller pieces that we happen to already understand. And that's basically the Hodge conjecture in its essence, right? It just so happens that when I say simpler pieces, they're definitely simpler than the original thing, but they themselves are also insanely complicated. So also a very interesting thing about the Hodge conjecture, sort of like a fun fact, if you will, is that depending on which expert, so, find a group of mathematicians working in algebraic geometry, which is kind of this field. Depending on who you ask, you will get a different definition of what the Hodge conjecture is, which I think really drives home just how complicated and abstract this is for the Millennium Problems. It's definitely the most inaccessible, but I'll do my best. So we're going to go into the world of topology. So in topology, a donut and a teacup are the same thing. If you've ever heard of topology, you probably know this because it's a very fun fact to sort of share with people. And the reason you treat them as the same is sort of what's shown by this picture and also by this animation, is that you can take your teacup and you can pull up the bottom, and then you can use the handle and kind of stretch it out to create your donut. And, and then you can reverse that process. I should reverse order of these pictures to make back the teacup. So the reason that we say they're the same is that when you're working in topology, what you're kind of doing is geometry without distances. So when we're doing Euclidean geometry, which is what you learn at school, you know, we're working with triangles, circles, squares, cubes, spheres, if we go into 3D. But distance is important. Like the concept of distance is very important. And we'll see this when I talk about the Birch-Swinnerton-Dyer conjecture. I'll be talking about triangles, and we'll be measuring the side lengths and the areas of triangles, because distance and therefore area is an important concept in geometry. It's not in topology. You don't care about the size or the distance between points. You care about their fundamental structure. So that's why a teacup and a donut are the same, because both of them have a single hole. The donut has a hole in the middle. The teacup has a hole in the handle. Otherwise, they are the same object. So shapes that are the same in topology, or they are deemed to be the same, if you can do what we call a smooth transformation from one of them to the other, or reverse. And when I say smooth transformation, there are certain rules as to what that means. The technical term for a smooth transformation is a homeomorphism. So that's probably a new word to most of you. That's a fun one for you. A smooth transformation is called a homeomorphism in maths. And basically what it's saying is you cannot tear your object. You cannot add holes, so you can't puncture it, and you cannot glue pieces together. So the way to think about it is really imagine your object was made of blue tack or made of Play-Doh. So if you have your donut made of Play-Doh, like we saw in the animation, it could be smoothly deformed. At no point were any pieces ripped off. We didn't puncture it, we didn't add any extra holes, and we didn't glue any pieces together. We just made a very gradual change by lifting up the bottom of the cup, and then we kind of smoothed it out to get the donut shape. So that would be a homeomorphism. That would satisfy the rules to be a homeomorphism. So if you can do this smooth transformation between the two things, then they are topologically the same. So I've got an example for you that I want you all to think about. We have a donut, again, like we've just seen, and we have an earthworm. And I would like to know, and this is going to be a poll, so click on the polls panel and cast your vote. Is a donut topologically the same as an earthworm? If you haven't got a clue, just pick whatever feels right. To a topologist, we've already seen that a donut is the same as a teacup on the first slide. It's very even so far, though it seems like no is edging ahead. So I can reveal the correct answer is in fact yes, I think, because here is a diagram of the anatomy of an earthworm, something I never thought I would ever learn until I was Googling this today. And what basically it shows is that the earthworm has a digestive tract, much like we do as humans, from its mouth all the way down to its tail and what's labeled its anus at the bottom. So an earthworm, theoretically, has a hole all the way through the center of its body, from its mouth to its bum. And so therefore, I would argue that it's topologically the same as a donut, because they both have a single hole through the center. Of course, this is a completely ridiculous example, but it's the kind of thing that you can play around with in this crazy realm of topology. And why abstract maths is quite fun. Now, so we have this idea of a smooth transition, a homeomorphism, where you can turn one thing to another, and then they're topologically the same. So given that we're allowed to do certain things, I also listed lots of things we can't do, right? I said you can't tear them. There are certain properties which are invariant to homeomorphisms. So when you do the smooth transformation, there are certain properties that won't change. Now, some of these properties, we've already seen one with the donut and the teacup and the earthworm, is the number of holes. So this is why you can't puncture your object and why you can't glue pieces together or tear pieces off, because that would change the number of holes that your object had. And that is a topological invariant. So that is something that isn't allowed to be changed when doing a homeomorphism. So that's one way of telling an object apart. So for example, a donut is always different to a football because a football has no holes and a donut has one. So they can never topologically be the same because they're invariant, their number of holes differs. So that's how you can tell things apart if one of their invariants has a different value. Another topological invariant is something called the Euler characteristic. And this is what I'm going to hopefully introduce a lot of you to, and what I'm going to ask you all to actually have a little, give you a question or two to have a play around with this for yourself, because it's quite fun, I think, anyway. So the Euler characteristic, it's a reasonably simple formula. So it's given by x is equal to v minus e plus f. And here, v represents vertices, or the number of corners. E represents the number of edges of your shape. And f is going to represent the number of faces. So your Euler characteristic is the number of vertices, v, minus the number of edges, e, plus the number of faces. And this is something that doesn't change when you do this smooth transformation. So if two objects have the same Euler characteristic, then they are potentially topologically the same, right? But if they have a different Euler characteristic, then they are definitely not the same topologically. So it's important to clarify between the two. Now I've got an example with a cube to show you how this works. So what we need to do is, first of all, count the number of vertices. So I'll give you 10 seconds for you all to think about this. How many corners does a cube have? Actually, if you want to write your answers in the chat, let me open the chat window. So how many corners does a cube have? You just need a cube and you need to get counting, or you need to try and maybe picture one in your head. So I would argue that the number of corners on a cube is going to be 1, 2, 3, 4 on the top. And then on the bottom, I think I'm also going to have 1, 2, 3, and then one at the back, 4. So I think there's going to be 8 corners on a cube. And I can see lots of people typing your answers. Thank you for joining in. So I can see lots of 8s as well appearing. So I think there are 8. We've got the 4 on the top and then the 4 on the bottom. So the number of vertices is going to be 8 for my cube. Now the number of edges, this is given by one of these sort of like white lines in my picture here. So an edge is going to be along the edge of the shape, perhaps what you might expect for an edge. So next, have a little think to yourself, how many edges does a cube have? And of course, be careful not to double count as well. So how many unique edges will there be on a cube? So I'm seeing lots of 12s. Well done for people saying 12. So you have 4 on the top, 4 on the bottom, and then you have these 4 vertical edges as well. So that's going to be 12. And then finally, faces. Hopefully we all know how many faces a cube has. If you've ever played with a dice, standard die, then you'll know that the number of faces of a cube is, of course, 6. So you count your vertices, your edges, your faces. You plug those 3 numbers into our formula for the Euler characteristic, and your answer is 2. So a cube has Euler characteristic equal to 2. And this, as I said, is a topological invariant. So if you have another shape that has an Euler characteristic that is not equal to 2, it cannot be topologically the same as a cube because it has a different number for the Euler characteristic, and that is something that is invariant, so cannot be changed through these smooth transformations. All right. Now, in order to calculate the Euler characteristic for a shape, there are certain things that we're allowed to do. And it relates back to homeomorphisms, these smooth transformations. We're allowed to deform our shape to give it edges and to give it faces. So we can push and stretch it into something that has vertices, edges, and faces, and then we can count them. And because all we did was push and stretch, we didn't add holes or anything else, because all we did was do a smooth transformation or a homeomorphism, remember the Euler characteristic is invariant. It doesn't change. So whatever answer we get after we change our shape has to be the same as the original shape we started with. So what I mean, for example, is let's take a circle. So I can turn a circle here into a triangle by just kind of squashing it a bit. And if I now count the Euler characteristic for a triangle, so that's going to be number of corners, V, is 3. The number of edges of a triangle, also 3, face. So the Euler characteristic for a triangle and therefore for a circle is going to be 1, because we've got 3 edges, 3 vertices, 3 edges, and 1 face. So a triangle has Euler characteristic 1, and because I can push and stretch my circle into a triangle, the circle also has Euler characteristic 1. So this is different to the Euler characteristic of a cube, which was 2. So a circle and a cube are topologically different. They are not the same object. Now, we can also do this with a sphere. So here's a little animation showing you how you can turn a sphere into a cube by kind of just stretching it out to fill the cube. So we want to calculate the Euler characteristic of a sphere. We just stretch it into a cube. We already calculated the value of x for a cube, which we got to be 2. So the Euler characteristic of a sphere is the same as a cube and is equal to 2. So if you have an object which doesn't have edges or faces or corners, then you can always deform it so that it does, and then you count up V, E, and F, and then plug your numbers into the formula. And that's okay as long as all you're doing is pushing and stretching. You cannot add or remove holes. That's really important to remember. Now, homework exercise. Well, it's not homework because you're all going to do it now, hopefully. I'm going to give you 3 shapes, and I want you to have a go at calculating the Euler characteristic yourself at home. So remember, there's the formula. We need the number of corners, V, or vertices, the number of edges, E, number of faces, F. So the first one is going to be a tetrahedron. And if you want to write your answers in the chat, that will be great. I'll give you a minute or so to work through these, and then I'll go through the answers. We're going to do an octagon. It's going to be your second shape that I would like to know the Euler characteristic for. And the third and final one is going to be a CD. And I want you to treat the CD as a 2-dimensional object. But the important thing about the CD is it has a hole in the middle. So I'll give you one final tip. So the first 2 hopefully are reasonably straightforward. The third one, if you have a hole in the middle of your face, it's not actually a face. Okay, so when we describe a face, such as the face of a cube or the face of a tetrahedron, it doesn't have a hole in it. So your CD does not have one face. You have to do something cleverer to turn it into a different shape. So as I said, I'll give you like a minute or so, have a think about this. As I said, please do join in, get yourself some pen and paper, draw these shapes and get counting edges and corners, and then I'll give you the answers in just a moment. So you just need to count the number of corners, V, for your tetrahedron, and your octagon, number of edges, E, and then the faces, F. Plug in those numbers into your formula, and then you should get the value for X for those first 2 objects. For the third object, for your CD, got to be more careful because you're not allowed to have the hole in the middle. So you have to do something slightly different to be able to solve that one. So I'm just going to go and have a look and see what we've got over here. So we've got 2, 1, 1, 2, 1, 0, 2, 1, 2, 2, 1, 2. I feel like there's a lot of agreement on 2 and 1 for the first 2, but then there seems to be varying opinions for the third one, the CD, the tricky one. So the tetrahedron, very well done for anyone who worked out that X is 2. The tetrahedron, in fact, is actually just the same as a cube and the same as a sphere. Because just like we turned the sphere into a cube by stretching it out, you could also have shrunk it down and got the pyramid, got the tetrahedron. So it's definitely 2 for the first one. And you can also get that from just counting the corners and the edges. The octagon, we've got 8 corners, 8 edges, and 1 face. So the answer is going to be 1 for the octagon. which I think a lot of you also got. Now the CD, this is tricky, because what you've got to do for the CD is, as I said, you can't leave the hole here. So what you actually have to do is turn, well, what I did anyway, the way I thought about it, is you turn the circle on the outside and the circle on the inside, turn them both into squares, which you're allowed to do. So now you have like a square with a square hole in the middle, but you've still got a hole in that central face. So what you then do is you add in diagonal lines between the corners. So you have your inner square and your outer square with diagonal lines joining the corners. And then what you've got is 4 trapezium-shaped faces. So you have 4 faces once you do that. And then you count the number of edges. So you'll have 4 around the edge, 4 in the middle. So you have 12 edges, 4 faces, and 8 corners. And so your Euler characteristic is 0 for the CD. If we have time, I can probably draw that out for you during the Q&A. But for now, I want to move back to the Hodge conjecture. But very well done, anyone who managed to get those. And thank you, everyone, for joining in. Okay, so we've talked about topology, this idea of smooth transformations between objects. We talked about that's called a homeomorphism. That's how you move between objects. And we have these properties called topological invariants that don't change when you move between between your objects. So when you do a homeomorphism, your topological invariants don't change. Okay, this is Mr. Hodge, by the way, William Hodge, after who the conjecture is named. So invariants we've seen. So we've seen the number of holes is an invariant. We've just looked at the Euler characteristic. That's another invariant. And there's a third invariant, which is relevant to the Hodge conjecture, which is called a cohomology class. Now, there is no way I can possibly explain in simple terms what a cohomology class is. All you need to remember is it's an invariant. It's a property of a shape that doesn't change when you do this molding and these smooth deformations. If you're really mathematically minded, it's a closed differential form. There you go. So we have another type of invariant, just like the two we've seen with the holes and the Euler characteristic. We have a third one. Well, there's actually many, but this one is a third one in our list called a cohomology class. The Hodge conjecture says, when can we construct a type of cohomology class called a Hodge class from simpler pieces? And that is about all I can give you in terms of the Hodge conjecture. So we're talking about topology. We're thinking about smooth transformations between shapes and this content and this idea of a homeomorphism. We've got things that don't change called invariants. The Hodge conjecture is all about trying to understand a particular type of invariant called a cohomology class. And it says, are certain cohomology classes built from smaller pieces, which are called, a certain type of cohomology class called a Hodge class, are those built from simpler pieces? And that's it. That is the Hodge conjecture in as much as I can possibly explain for you this evening. So that brings us back to voting. And I believe there's only going to be one left, which is going to be the Birch and Swinnerton-Dyer conjecture. So I'm guessing maybe we do still have a poll, but obviously there's only one option. So just to recap, I mentioned this is all to do with objects called elliptic curves or elliptic equations. And what we want to know is the number of rational solutions to a particular elliptic equation. And by a rational solution, we mean either a whole number solution or a solution that can be written as a fraction. So that's literally what it says. It says, is there an easy way to tell the number of rational solutions to a given elliptic equation? And this is really important in cryptography, elliptic curve cryptography, which is used in iPhones. So as I said, you have interacted, the vast majority of you will have interacted with this in your lives without realizing it. So we're trying to understand these elliptic curves through this Millennium problem. Okay, so to start off, I'm going to give you another exercise and another, let's call it piece of homework. And it's actually, what we're going to do is look at a puzzle that used to entertain the ancient Greeks. So the thinkers and the philosophers and whatnot of ancient Greece used to entertain themselves with this exact puzzle. And it's to do with triangles. Two really important triangle theorems written for you there, just to remind you all. So if you have a right-angled triangle, sides A, B, and then the diagonal is length C, then first of all, Pythagoras' theorem says that A squared plus B squared is equal to C squared. And also the area of your triangle is 1/2 times the base A times the height B. So both of those two things are satisfied by a right-angled triangle. Now, the ancient Greek puzzle goes as follows. If I give you a positive whole number, let's call it D. So I give you some number D, then your challenge is to find a right-angled triangle where A, B, and C are all rational numbers. So they're all either whole numbers or fractions, such that the area is equal to D. And what I want you to do is to try and figure this out for D equals 6. So I would do D equals 6 first, because it's much easier. And then if you're feeling really adventurous, try and come up with a solution for D equals 5. And again, if you want to write your answers in the chat, that'd be fab, so I can see how everyone's getting on. So again, to go over this, I'm saying I want you to find me a right-angled triangle which has area equal to 6. And it has to be such that A, B, and C, so all three side lengths, have to be either whole numbers or fractions. So they can't be pi, they can't be the square root of 2, they can't be irrational numbers. They have to be whole numbers or fractions. So first of all, I want you to try and do this when the area, D, is equal to 6. And then if you're feeling really adventurous, try and do it for D equal to 5. So 5 is much trickier. 6, hopefully, a few of you can figure out. So I can already see some answers coming through for the D equals 6 case. I'll give you about 30 seconds or so to have a bit more of a think about D equals 5, because I am going to show you the answers, so I don't want to reveal them too soon in case people are trying to figure this out. So we want A, B, and C to be fractions. They are fractions for D equals 5. I'll give you that. We want A, B, and C to be fractions so that the area of a triangle is 5, and A, B, and C are all indeed fractions. But well done, anybody who is, I'm seeing lots of correct answers for D equals 6, so very well done. Not sure if I've yet seen an answer for D equals 5, though I would be insanely impressed if anybody was able to come up with it in such a short time limit. So if you don't want to know the answer, I guess look away now, because I am going to show you the answer. So for D equals 6, a lot of you have written the answer. It's what's called a 3-4-5 triangle. It's a very famous Pythagorean triple because it gives you 3 whole numbers that satisfy Pythagoras' theorem. So 3 squared is 9, 4 squared is 16, 5 squared is 25. So A squared plus B squared is indeed C squared. And then the area of the triangle is 1/2 times 4 times 3, which is 6. So that's there probably are other answers, but that would be one of the correct answers for D equals 6. Now for D equals 5, much more difficult, but this one will work. So you can have a triangle with 3/2, the height, so 1.5. Along the base, it's 20 divided by 3. So when you multiply those two numbers together, you get 10, and then you divide by 2, and the area is indeed 5. And when you plug these two numbers into Pythagoras, it tells you that the diagonal is 41 divided by 6, which is also a fraction, of course. So D is much trickier, but this is a very rich area of study, and there's lots of interesting triangles you can try and come up with and sort of triangle problems based around just these two simple rules, Pythagoras' theorem and the area of a triangle. Now, other than being fun, this is actually very relevant to elliptic curves, because to actually solve this problem, it turns out what you're solving is this equation. So if you can solve y squared equals x cubed minus d squared times x. So if you solve that for x and y, where x and y have to be rational numbers. So x and y are whole numbers or fractions. If you can, and d here is the number, right? D is your area. So we just did d equals 6 or d equals 5. So you plug in your value of d, and then if you solve this equation for rational fractions x and y, then you actually get the answers for your triangle lengths a, b, and c. And the way it works is as follows. So here's my triangle ABC. So you set a is equal to x squared minus d squared divided by y. So again, we know d is given to us from the area. X and y are the solutions to this equation that we have to find. It's tricky to find x and y, but if you solve that equation for fraction x and y, then we know those values. So a is x squared minus d squared over y. B is given by 2xd divided by y. And c, your diagonal, is then x squared plus d squared, all divided by y. We can check that this works, so we can plug it into Pythagoras' theorem. So this says this will only be a right-angled triangle if a squared plus b squared equals c squared. So if I do a squared added to b squared, it looks like that. If I now expand out that first bracket, I'll get x to the 4th minus 2x squared d squared. But then I add on 4 x squared d squareds. So what it turns into is this x to the 4th plus 2x squared d squared plus d to the 4th divided by y squared. And then finally, you look at this formula and say, oh, but that's exactly c squared. So that's exactly equal to the value of c squared. So this does work. So if you take this to be a, b, and c, it satisfies Pythagoras' theorem. And then we also have to check that it satisfies the problem for the area. So the area tells us that we must have a half times a times b must equal d. So again, we're going to take a, we're going to multiply it by b, and we're going to divide by 2. And hopefully that will give us d. So at first, it doesn't look very promising. So that is a times b divided by 2. So first of all, the 2's cancel, which is the first thing to spot. Once the 2's have cancelled, what you do is you take the x inside the first bracket. So now it's x cubed minus d squared x. And then you leave the d outside. Because now what we've got is d times x cubed minus d squared x, all divided by y squared. But we haven't used the equation at the top yet. So we solved x and y, so they satisfied the equation in the black box. So what we know is we know that y squared is actually x cubed minus d squared x. So if I put that on the bottom to replace the y squared, they perfectly cancel out, and you're just left with d. So this is a different way of solving the triangle problem. So trying to do that ancient Greek puzzle about can you find a triangle with rational fraction side lengths, area d, turns out, and this happens all the time in maths, it's exactly the same problem as trying to solve this equation for rational or fraction x and y. And that's sort of, I've gone through this very quickly, but this is how you show they're actually the identical problem. Now this, in the box, this is an elliptic equation. So this is what that ancient Greek triangle puzzle has to do with the $1 million Birch Swinnerton-Dyer conjecture, because this is actually a special case of an elliptic equation. So elliptic equations have the following form. It's y squared is equal to x cubed plus something times x plus b. So in our example on the page before, we've got x cubed, we've got that a is equal to minus d squared and b is 0. So a is minus d squared, b is 0. Therefore, we have exactly an elliptic curve. Now, they give you some pretty funky graphs, in all honesty. So here's an example of one. particular elliptic curve. So I think this is for a equals 1 and b equals 1. So they're pretty cool shaped graphs, right? Because you've got a y squared, you've got an x cubed and other things happening. So it looks like this. And in fact, what you can now do is if I decide, so I have a value for a, if I fix that value, right? So if I fix a, and then b in this picture is positive, and if I start to now decrease b, so if I fix a and let b get smaller and smaller, it's going to eventually decrease to 0, and then it will go negative. So if you do that, as I've done in this animation, this is what happens. So it starts with our squiggly shape, and then as you decrease b, it kind of pinches off. So those two bits join together and creates like an island almost of an ellipse, which is maybe why it's called an elliptic curve, in fact, here, which then shrinks away as you keep decreasing b. So you can play around with these things. They're very cool. If you just sort of, play around with your favorite way of plotting graphs and try different values of a and b, you'll get lots of very interesting shapes. Where you have, sometimes it's one piece and sometimes they're in several pieces. So elliptic curves, very, very interesting objects. And as I said, sort of were originally, can be related back to this ancient Greek triangle problem and are really important today in cryptography. So the Birch-Swinnerton-Dyer conjecture then, this is asking that for a given elliptic curve, so if I give you an elliptic curve, which has to, remember, have that form, y squared is x cubed plus something times x plus something. If I give you an elliptic curve, the Birch-Swinnerton-Dyer conjecture says how many rational points lie on that elliptic curve. So how many points are fractions for both x and y. So again, it's very similar to our triangle problem at the beginning. So let's take an example. So here again is an elliptic curve. If I were to draw the line x equals a half, right? So that's this blue line down the page. So that is definitely a rational number. Then what the Birch-Swinnerton-Dyer conjecture is asking is, first of all, you draw this line for some rational number x. I've picked a half. It could be anything. It intersects our curve at 2 points. Let's call them y1 and y2. And then if we draw those lines, y equals y1, y equals y2. So now the question is, x is definitely a rational number. It's a fraction. Is y, or is either y1 or y2, or maybe both, are they also rational numbers? Can they also be written as a fraction? So you pick a rational number for x, draw your vertical line, find out where it intersects, and then read off those y values. If x is rational and one of your y values is also rational, then you have a rational solution to your elliptic equation. You have a rational point on your elliptic curve. And that's really what we want to know with Birch-Swinnerton-Dyer. But instead of going through this very laborious process of drawing lots of vertical lines for different fraction values, we want to know, is there a shortcut? So if I just give you an elliptic equation, can you very quickly tell me whether or not it has an infinite number of rational points or just a finite number of rational points? So we think we know how to do this, and this is the conjecture itself. We have something called the Razavi L function. Now, the study of L functions in itself is a really active current area of research. So we don't yet know everything about L functions that we would like to know. However, we have this particular L function called the Razavi L function after the two people who worked on it. And what we think, or what the Birch-Swinnerton-Dyer conjecture says, is if you take an elliptic equation, which remember is y squared equals x cubed plus ax plus b. So take any elliptic equation, plug it in to this function. So literally think of this as a function machine. You feed in any old elliptic equation that you've made up. Pick a value of a and b, plug it into the L function. This will give you one of two possible outputs. it will either give you 0. If the output is 0, that means there are infinitely many rational points on your elliptic curve. If it outputs 1, I believe, no, sorry, if it outputs non-zero, so if it outputs 0, you've got infinitely many rational points. If it outputs anything else, then there are only finitely many rational points. So this looks like the perfect way to test how many rational points are on any given elliptic equation. Plug your equation in. If you get 0, there are infinitely many. If you get a non-zero answer, there are only finitely many. However, we think it works. It's been tested on millions of different elliptic curves, and it gives us what we expected to get. However, as with all things in maths, just because you've tested it a lot and it seems to work doesn't mean it's true. So the $1 million question, to get your $1 million, you've got to prove this. So you have to prove that the Hasselbalch L function will in fact determine the number of rational points for any given elliptic equation. And with that, that will be all 7 Millennium Problems done in 2 Royal Institution live streams. So thank you very much, everyone, for sticking with me. I know those 3, if you were here for the first one, I'm sure you're like thinking, wow, those 3 were like next level abstract. But I hope you've been able to follow as much of it as possible. I tried my best to try to explain them all as simple as I could. But those 3 are by far the most difficult to get your head around, right? The first 4 that we did are sort of embedded a bit more in reality. All of these 3 are really, really abstract. But I hope you'll agree they are super cool maths and, really interesting problems. So I believe we're going to do a Q&A. So obviously stick around if you have any questions. But again, thank you very much for joining in. Thank you for voting. Thank you for taking part in the chat. It's been great. I've really enjoyed it.